Thanks everyone for coming. Today, Sid and I will present getting user-facing analytics for the Web3 at scale. And first, let's Sid take the stage to talk about Magic Eden and their use cases.
Okay. Yeah. Thank you, Sean, for introducing me. Maybe I'll tell a little bit about Magic Eden and tell a little bit about NFT. So Magic Eden is the leading NFT marketplace in the world, and we are about 2.5 years old. We are a cross-chain marketplace, so that means that ultimately we simultaneously operate on many blockchains. So currently we are on 5 chains, and we expect to double the number of chains this year. And so this also means that at any given time we generate a lot of activities, both on-chain activities, so settlements of trade, as well as off-chain activities like listing, putting something up for sale, and then bidding, making a bid for an item. The use case of Magic Eden, as you can imagine, is very much as a real-time trading platform. And so the real-timeness of data and analytics is really important for users to make purchasing decisions. And so a little bit more about us. We're the #1 NFT marketplace across basically every chain. So this is last month data. We're on Solana, Bitcoin, Ethereum, Base, Polygon, and we're #1 on every metric. What I'm actually saying is, and so at any given day, we're about 70 to 80% of the NFT market. And so we're generally approximately about 4 to 5 times the size of OpenSea now. OpenSea used to be a leader. What I'm actually saying, this is a long way of saying that we're hiring engineers. And so if you're interested, my email's here, and we also have Wei Qing here. Please come talk to us. Cool. Okay, so I would love to talk a little bit about why real-time analytics is important for Magic Eden and important for trading as a use case. And I will actually talk a little bit about the example use cases in the next couple of slides. But you can also imagine that we need to help make users make real-time trading and purchasing decisions, but not just purchasing, but also selling decisions on a market that's very, very dynamic. And so beyond that, there's something that's quite unique to Web3 and blockchain-based businesses, where in blockchain technology, all data is public and shared. So as opposed to in the traditional world where every platform owns their data and the data is the proprietary, where proprietary competitiveness comes from, in Web3 and in blockchain, all data is public. All the important data, or like the trade settlement data is public. And so this actually creates some very, very interesting dynamics. So for example, anyone can create a real-time analytics platform using Magic Eden's trading data. And Magic Eden can also do real-time analytics using our competitors' data or on anyone else's data. And so in fact, the analytics of trading actions are global across all trading, from all marketplaces, on all chain. So in some ways, I think maybe an analogy is like every technological platform creates new ways to create moats and competitive moats, but it also creates new competitive surfaces. Like the internet make geographic advantage irrelevant, but then it create a competitive surface on proprietary data. In Web3, there's no proprietary data on chain, which is all the settlement data and your trading activity data. Everyone sees everyone else's data. So that means that not only we have to just provide the fastest and the best real-time trading analytics experience against all our competitors, and that's the additional competitive surface that we have. And so, as an example, there was actually a time where the real-time analytics of our trading was slower than the real-time analytics of our competitors. Sorry, our competitors' real-time analytics of our data was faster than our analytics of our data. And so, first of all, that's a problem from like a product competitiveness standpoint, but it's also kind of embarrassing. So and so from here on, that's kind of the motivation to revamp how we do analytics. And so maybe I can start with just talking a little bit about the use cases, example use cases. So this is collection discovery. It's you can imagine this is like every collection is about 10,000 items. And we have the current floor price, which is the cheapest listing in any given collection, the total volume, so how much money has exchanged. So for example, like for the first item, Boy Yacht Club, the total volume is 4.8 billion US dollars. Of course, there's market cap, offer, the changes, per day, and so on and so forth. And we also have collections that are new where you don't have the one-day change because it's a new collection. And so this is basically to help users to find out which collection has the most significant changes given the past time range, as well as help users discover and pick interesting NFTs, and as well as it's about discovery. This is our collection trading page, and so on this page, these are all the listings that are on the platform, how much they're listed for, and beyond that, you can imagine this kind of trades like sports trading cards, right? Like, and this is like a digital version of that. And you can see that on the top banner we have some aggregate, high-level aggregate metrics, and then on the right-hand side, you can see for example, like top traders in the last 7 days, and we have aggregate volume. And our goal is to make all of these numbers as real time as possible. And of course, we have some caching on top of it, but they have different cache duration. But the goal is definitely to make it as real time as possible. Especially when a collection just drops or there's some new event happening and trading is happening really quickly, we want the numbers to update in real time or near real time. And then there's charts. A floor price time series is basically a historical record showing the lowest available price of any given collection, and it provides insights into the minimum cost of purchasing one of these items across different dates. And so this helps identify trends, understand market dynamics, and so we have both like the floor price as which is a time series data, as well as volume collected over, like in this case, the 1 hour interval. And so analyzing this time series data, it helps traders to make trading decisions. So maybe I'll talk a little bit about what we did before Pinot. So before Pinot, the pipeline was using Databricks, and that I make that decision really early on in Madge Eden's lifetime. We started using Databricks very early because I was using Spark at Uber, which was my previous job. And my thought process was like, we'll start with a Spark ETL right into cache, and then over time we'll explore Spark streaming. And that was certainly how, at least when I was at Uber, there was a lot of real-time analytics pipeline was done using that approach, at least in the org that I was in. And so essentially that snapshots of materialized view, write to Postgres is caching for the query. But the pain point was, number one, in order to create new stats, someone has to write a new PySpark job, which is not super hard, but you still have to learn it. And it's like a whole different tool chain. Second was, we did not use Spark streaming at that time. So the ETL job had a 5-minute data latency, but we were exploring, Spark streaming to reduce latency. And the cost was fairly high. And so maybe I'll talk a little about what we end up doing. Essentially in the middle is we'll write in Kafka in real time into a real-time table, which then Xiang is going to talk a little bit more about, like the architecture on the StarTree side of how then it writes into the offline table, which gives us further scalability and also like cost. It's more cost efficient. And then we have a cron job that pushes it into Postgres cache. And of course, like because Pinot itself is very, very scalable and really fast. This also allows us to really tune our cache interval to be a very, very low interval. And in the end, we finished migration. This was really good. It's probably one of the only technological choices that we made in the last 12 months that had no compromise on all dimensions, where it was a lot easier for developers to work with because you're writing SQL. data became a lot faster, and right now, like for some of these endpoints, we're using like a 5-second or 10-second cache interval, but we're actually looking to working towards like even reducing that even further for certain more time-sensitive endpoints. And the savings was extremely significant. But beyond what's quantitative, what we can kind of measure quantitatively here, anecdotally, it's just easier. Like it's like less problems. You don't need to think about that much. The code is simpler. So like when we add new features, there's less bugs. There are a lot of things here that is not easy to quantify, but actually it impacts. It's like the invisible hand that really impacts developer productivity. And I think beyond developer productivity, also developer happiness. The amount of complaining that I hear is a lot lower. And I will let Xiang take over from here. Thank you.
Yeah. So thanks, Sid, for making all the introductions and giving the high-level architecture and overview of what we are doing at Magic Eden along with StarTree. So I will take it from here. So this is like our data model when we try to tackle this problem. So for this problem, I try to like simplify all those like data model as simple as possible. So this is the normal event we are tracking is just the transaction activity. It means that we have some hash, which we can consider that as a primary key, and we have timestamp. Collection ID is like the NFT ID, and then we have like different type of transactions. We have the currency amount, block time, and if you look at the schema, there the bottom two lines. There's one is called is worth trading, and the other is deleted. So these two things are like the major things that we want to model, because for the blockchain data, although it's like on-chain data is immutable. However, from the trading platform perspective, we also want to solve the problem that detecting if this is like some worth trading event. It means that some people, they are trying to fakely make their NFT transactions or their collections looks beautiful. That's why you want to exclude those things to help the real traders to get the correct data. And in terms of the building the product and this kind of the collection discovery page, we need to have a different time range of the collection cell volume snapshot, right? So for example, we want to say past 10 minutes or past 1 day, 7 days, 30 days, what are those collection cells volume? And here is like one simple SQL based on the schema we are providing. And say it's like just do select aggregation with some predicate and then group by. From the predicate perspective, you can specify this is my time range so that you can say, okay, this is my 10 minutes snapshot. However, if you think of this is like a simple schema and a simple snapshot, what are the challenges to ensure your results is correct? So the real challenging here is to solve the data correctness problem. So here, from the whole end-to-end pipeline perspective, think of your data producer. If you restart it, it may rewind the offset, try to regenerate something, publish to Kafka, then you have duplicates. How do you solve that problem, right? And think of like later on, you may find out, okay, there are some events happening, I want to revise the data, and then you push down some other event with the same transaction hash. And another is something like, okay, maybe there is some problem with my upstream data producer, and I want to really delete some data. So all those things happening, and of course, there will also be like the out of order events, which means that you're actually publishing some older events, and it may actually override your new events, right? So all those kind of things are happening, and if you look at here, we want to really update the last two fields. So this is like a perfect use case for Pinot upserts. So Pinot upserts is nothing but just still following the Pinot's architecture of like just do appending to the Pinot logs. But the difference here is we're also implementing one thing called the upsert metadata. This is just the way of like keep track of the primary key to the record location, which is nothing but a segment document ID, and as well as there were some timestamp associated, so that you will know that if there's older events coming, you won't really override the data. From the query perspective, Pinot side will have something called a valid.id bitmap. This is for fast filtering, so that it's also updated during the upsert, so that your query time you won't do like the merge on read. It's always like pre-computed already. The last thing here is like because this is a log structure, append log structure, and based on the upsert, gradually you will find a lot of holes, and a lot of older data is like not really queryable or usable, so that the compaction could happen later in an async manner. So this would be like one example of how we do the upsert. So if you look at the top row, it's like the updated timestamp is like when the events is happening. If you think of it, it's like just 3 events with like 3 snapshots of the data. And here I just mimic a very simple example. It's like the snapshot version 0, let's say is deleted is false and is worth trading is false. And think of your record, the location is in segment 1, document 0 with some updated timestamp. And if you think of the valid doc IDs, right, when a query comes in, it will always query the first valid document. And now you have a new event coming, which is the middle one. It says it's worth trading is true. And the doc ID is 1, right? So in this case, you will find the valid doc IDs becomes 0, 1. It means that the first document is invalid already. And think of the last records coming. Let's say if this record is getting to a new segment. In terms of that, it will invalid all the valid doc IDs from the first segment, and just the second segment will have a valid bitmap. So another thing here we want to show is we do a lot of drawings at real time. This is another example of like, because think of like we have a lot of upsert table. It means that a lot of dimensional information may be updated. And before drawings, usually the way we're doing things is like we do pre-drawings. We do like a very big wide table. For this wide table, the good thing here is like the query is, when you write the query, it's simple. However, the downside here is like whenever there will be there is a major dimensional change, you actually need to go back and rewind a lot of data. So in Pinot, we do implement drawings in the new multi-stage query engine. And the best of it is now it's supported the shuffle hash distributed drawing, along with the broadcast drawing as well as the lookup drawing. So this will be like one example of like we want to do drawings at the real time. If you look at here, this is actually like one way to compute the floor price. And the major thing here is like is using a dynamic filtering to boost the query from pretty much like a full table scan into inverted index lookup. This is trying to like find the floor price of the latest timestamp. So it will try to first find all the maximum timestamp of those collections, and then just use the lookup to get those aggregates. So we also did a lot of like performance improvement in terms of like getting the query latency in hand. So the first thing here is like, of course, the inverting index, because a lot of queries we do have like the collection IDs in the predicate, right? So Pinot internally have this like bitmap based inverting index, which is like very textbook kind of solution. And here, the query latency is always proportional to the number of documents that you are scanned. So in terms of that, if you think of this like NFT data or like this crypto data, the one major thing here is, so for those like collections with small view or small traction, it will be fewer people querying that. And although the query latency will be good, however, if you look at the real problem is like people are mostly care about the popular collections, and those popular collections have a lot of data. So it means that when you are querying, you will see majority of the people querying like the large data, large query with huge latency, and those small amount with good latency data, people don't really care. So we also introduced something called the pre-aggregates StarTree index. So this is a perfect solution in terms of solving the problem of like for the query that will hit a lot of data, we can use StarTree index to pre-aggregate those values so that at the real time, at the query time, it will mostly be the runtime lookup. So for example, this is one example of, let's say, if my collection 1, 2, 3, 4 is like is a very popular kind of collection, then we can pre-aggregate those volume beforehand, and then when the query come in, I'll just get the results. So for this pre-aggregation, it's also like a trade-off between the space versus the latency. You can always tune through this curve line based on like how much space you want. You can tune based on this maxed leaf record. It will help you to get to reduce the number of doc scan. So here is like a rough number of the latency improvement. So without any index, think of like a simple query can just run with like more than 2 seconds. But with inverting index for the very top collections, it will drastically reduce, but since the query may still hit, let's say 20% of the data or like 10% of the data, so your latency will still be like a couple hundred of the millisecond, right? So, but with the StarTree index, with like those kind of pre-aggregates, it can drastically reduce the query latency. So the last part we do here is for the Lambda architecture. The real problem of the indexing here is that StarTree index doesn't work with upstart table. So in terms of that, think of my data span is, let's say, more than 3 months. And I will try to model the data with, let's say, past 7 days in real-time upstart table, because I may still detecting some fraud or some activity. I want to modify the data, so I want to put the latest 7 days data in the real-time upstart table. But for any data that past 7 days, I will try to move it to the offline immutable format, which I can actually use StarTree index to boost the query performance. So this is what we call it as the Lambda architecture. And in terms of that, the Pinot broker will be able to track all the largest queryable timestamp from the offline table. When a query coming, same query coming, if you look at here, the Pinot broker will try to append a time predicate to split the query, and the latest data, the latest query will hit the real-time table, and for all the rest things, it will hit the offline table. And also, we try to preferably let Pinot broker to query offline table more than the real-time table, so it can relieve some kind of query pressure, the CPU pressure, as well as because we have StarTree index at the offline table, so the query latency will also be better. So we want to query more data from the offline table other than the real-time table. So from the cost-effective perspective, we also have the implementation of something called the RocksDB-based off-heap upserts. So this is some StarTree implementation of the upsert. So Previously, I've talked about there's something called upsert metadata. That one was purely on heap implementation from the open source perspective. And from StarTree side, we have one implementation of the RocksDB based on disk of heap implementation. So we have now our very preliminary like a benchmark on the AWS EC2 instance of the i4i 2x large, which is 8 core and 64 gig RAM. So for this kind of use cases, we can support only 50 million primary keys if it's on heap, but it can scale up to 1 billion primary keys in the off-heap mode. So this means that if your data volume is primary key bounded, then you can actually scale 20 times more data into one machine, other than like you need to put like 20 machines to serve the use case. The other thing here is we also have this kind of, we call something called the table level snapshot. This snapshot is majorly for Pinot Bootstrap. So the thing here is like, because we need to build a valid doc.id set, this is like a bitmap. And from the Pinot perspective, there will be like many segments, right? So in terms of building the valid doc.id set for query, you need to scan every segment and then try to merge and get the table level valid doc.id. So this thing become extremely slow when the primary key size is very large. So if you look at the number for just one partition with close to 50 million primary key, without this table level snapshot, just by scanning segment by segment, it may take like 16 minutes to start this partition before you can query this table. And after the snapshot, it will just be like 10 seconds-ish. And here we also talk about some future work that like majorly inspired by the Magic Eden use cases and their asks. And so first of all is about the PostgreSQL WAR protocol. So one thing here is we want to see how we can integrate more data tooling and visualization solutions, especially like Looker, Tableau. So in this case, it's our thinking here is like we will try to build something called the Pinot Postgres proxy, which in front of Pinot will translate, will speak the Postgres protocol, so that you can use Postgres client to talk to this proxy, and this proxy internally will convert the query to Pinot. And also it will be simpler for integrating with like Looker or Tableau, those kind of database tooling. The second thing here, as I mentioned, that StarTree index doesn't work with upsert, right? So this is something we are also going to do to support upsert, to support the StarTree index inside the upsert table. So if you think of here, the majority motivation here is I don't need to set up two tables, one for upsert real time, one for the offline table. I just, so for majority of the use cases, if the data volume is not that large, or you don't have like huge kind of data rewrite requirements, then probably just one upsert table is good enough to just for the simple setup. And the other thing here is like, since you have all the pre-aggregates, so the query performance will be actually boosted a lot from the upsert perspective. Yeah, so yeah, that's pretty much for the talk today. Yeah. Thanks.
And I think, are we gonna accept any questions from the audience?
Oh, yeah.
Yeah, all right. Do we have any questions from the audience? And just raise your hand if you have something. I'll come up with microphone. And you can ask your question, yeah. I'm coming to you.
If you want, come.
No, just I'll hold it for you, yeah. I'm also controlling time because people thinking I'm weird. No, I'm not weird. I'm just trying to Be cautious on time. Sorry. Go ahead.
So Sean, we have a similar setup where we have an offline table. We roll every night, push it in, and then we've got an online real-time table that is upsert as well. You had mentioned about the snapshotting. Do you snapshot when the application is coming down, when Pinot is coming down, or is that like a scheduled time snapshot?
You mean do you mean this?
That right.
The number
RTA.
2, right? Yeah, this is the new feature that we implemented probably 1 or 2 months ago. So this is called upsert snapshot creation task. It's per table basis. It means that it will run in a minion. This minion will look at the RocksDB locally, right? So for each table partition, it will try to generate the table-based snapshot. And also it will look at, let's say, the segments. It will pretty much like include all the segments that within this snapshot, so that when you load this snapshot, you actually load the entire thing. It may contain, let's say, 100 of the segments. So that's how we can bootstrap. And also this is like we load all the SST files from the RocksDB. And after that, we can also apply the diff. Let's say if your data retention kick in, you deleted some segments, and those segments will be removed to update the value.id. And also if your new segments has come in, and then it will be like a few segments, probably just for today, and then to update the value.id set. And also this thing, we usually take, let's say, once per day for this snapshot to run. Also, we keep this snapshot in on S3 so that it can always be downloaded and to bootstrap everything. Correct.
Yeah, I'm interested in the cache that you built using Postgres, going from Pinot into Postgres. I imagine that is to reduce the latency for like serving the website. How do you handle that? Do you requery every potential cardinality of that, or are you just picking and choosing where you think you can, or that you think needs to be updated, and like how do you manage that cron job?
Do you mean how to populate this cache, or okay? So probably Sid can answer this. So my understanding here is like there will be a cron job, periodically query Pinot, and populate the snapshot results into this pSQL cache, and then there will be APIs wrap on top of this pSQL cache. See if you have any.
Yeah, so yes, basically that. We run for endpoints that are not not as latency sensitive. So we query, I think we have a cron job that runs every 5 seconds, and pre-populate a pSQL cache. But I think we did load test that if we want to go to completely real time, we can also hit Pinot directly and it's fine. But we wanted to, am I correct to say that? Oh, right. Yeah, sorry, I forgot. We also have some other like configurations that we want to join with. And doing it then inside pSQL made it easier. So like, for example, like the ops team might say, hide these collections metrics because there's a violation of policy, like things like that. That's why we did the cache. I think actually in terms of just scalability, we can just hit Pinot directly and it's fine. Okay, yeah.
Cool. You mentioned the use of upsert table. Is that on, and then I think in one of the slides, you also mentioned there's a 10-minute kind of collection rollup. Do you enable upsert for all those or just the raw transaction?
Do you mean here? Oh yeah, so this 10 minutes rollup is based on this transaction, right? So think of your Pinot table as a kind of log-based table. It tracks all the activities of the on-chain data. And now you want to show, let's say for this collection, 1, 2, 3, 4, what's the past 10 minutes of volume, right? So if you want to show this thing, the thing here is like you need to run this query on your activity data. Then you can generate this snapshot, right? This is like your query.
The upsert is only enabled for the TX activity.
Yes, the upsert enabled for TX activity, so that, for example, I want to exclude all the wash trading for any collection, right?
The upsert period is 7 days. We kept the upsert table 7 days, so within 7 days we can go back and change the activity. That's the design goal. And the reason, the business goal is because the certain trades, once they get settled, the status can change, or sometimes we just have a bug. And so the upsert table, actually a lot of times it's because we have a bug, right? If we have a bug, we need to go back and fix the data, and we're essentially allowing ourselves 7 days to fix if we have bugs. So it's, yeah. And sometimes the upsert is because of, sometimes the blockchain itself can reorg, and certain transactions that went through in the past actually then get reorged out, and that can happen in the first hour. So those are the examples of where, like, even though the data is supposed to be append only in spirit, but in practice, there's a small percentage of data that needs to be fixed or needs to be repaired, and we allow ourselves 7 days to repair.
One last thing. So is this the data that you materialize and put it in the P-SQL cache, or do you store this in Pinot, the 10-minute collection roll-up?
So I think that this 10 minutes snapshot numbers are in the cron job that can be that's calculated from the Pinot and put into the cache.
Quick question. When are you planning to release the Postgres proxy for Pinot, and will you support JSON-B from day one?
So the timeline here is in next 2 quarters. Yeah. Huh? JSON-B? Which one?
Yeah, JSON-B type in the Postgres.
That part I need to look at. Yeah. Yeah. Right now, the WAL protocol here is to ensure you can use, let's say, Postgres compatible client to write query into Pinot, but still, this is like still Pinot query. You cannot write, let's say, Postgres syntax. Right, so for that part, we need more time to do all the conversions and make Pinot to be. I see. For those kind of things, we need to ensure this like UDF that's being implemented in Pinot as well. Yeah.
It's over here.
So this is a question regarding the future work on upsert table StarTree index. Would there be some kind of re-indexing time period for all the re-aggregations, as well as does this mean if we have the StarTree index on the real-time table, it will need to consume more machine power?
In short, yes. So because the computing of the pre-aggregates will be more comparing to offline table, because you need to update the previous segments and you need to update the new segments as well. So definitely it will consume more CPU power, and we will share the design very soon, so to the public. Yeah.
Xian, Sydney, thank you so much for your time. Thanks so much for being a part of Real Time Analytics Summit.